Everybody, and welcome to our next mathematics curriculum convo with myself, Pete Mattock, and of course the main person of the evening, Lucy Rycroft-Smith. She pays me to say that. And we're joined today by our very special guests, Gemma Sherwood, Will, what's that surname, Will? I can't read it.
Marler.
Marler, thank you. Jeff Wake, of course, and Andrew Stacey. Do you want to just say hello and a little bit about yourselves, guys? Gemma first.
Hi, I am a senior lead practitioner for mathematics at the Ormiston Academies Trust, and I've been teaching maths since 2004.
Will?
My name is William Marler. I'm an animator, currently working on a project called Learn with Will, teaching science, English and maths in animated videos.
Thank you very much. Jeff?
And I'm Jeff Wake, and I lead the research group at the University of Nottingham in maths education.
And a recurring guest for us, of course, Andrew.
Hi, I'm currently a maths teacher in Oxford and formerly a university lecturer in Norway, amongst other places.
Fantastic. Thank you all very much. And our chat today, of course, is are fractions, decimals and percentages just ratio, which was proposed by Lucy. So I'm going to come to Lucy to start us off. Lucy, what do you reckon? I assume you proposed this because you've got some form of opinion about it.
No, not really. I'm kidding. Jokes. I read this. I read this in a paper, and it's a Jerry Confrey paper from 2001, in which not only do they tentatively, I don't think they use this exact phrasing. I think I've been a bit controversial. I don't think they.
It's not like you at all, Lucy.
I don't think they propose that all fractions, decimals, percentages are just ratio, but they suggest that ratio is. I'm going to say exactly what they say, just so I don't slightly over-egg it. The multiplicative notion of ratio provides the centre of the model. So all the other forms of proportional relationships and representations get taught to some extent through the lens of ratio and by their relationship to ratio, which is an interesting one because it's not really the way we do it here. And it is a bit of a mind bender to think about how that could happen, because to some extent, I think if you've taught maths in England, if you learnt maths in England, you may have ratio as the hardest and most complex of the representations we're used to of proportion, so fractions, decimals, percentages, and should be dealt with last, whereas actually their proposition is the opposite of that. So I'm intrigued by it. I wouldn't necessarily I'm persuaded by it at this point, but I do find it interesting. And if you don't know Jerry Confrey's work, she does a lot of research where she sort of proposes ideas, learning trajectories, and then tries them out in the classroom and reflects on them and evaluates the model. So this isn't a researcher who just does theoretical work. She does a lot of really using it with real children in real classrooms. Gosh. A researcher in the wild.
Do you have a link to that paper, Lucy?
I do, yeah. I can pop it on Twitter while Jeff vehemently disagrees with me.
Well, I was going to come to Jeff next, actually, if that's all right, because Jeff, obviously, you've got a very, very large research background yourself, and I wondered what your take on this was, and whether you find your research and research that you've read agrees, disagrees, has alternative views.
Well, I wouldn't disagree that she said that in a paper. But I'm not sure that I agree with starting with working with fractions and decimals and so on from ratio. Why did she? I mean, Lucy, you might be able to help us see why she would possibly say that.
Well, okay, so the paper suggests that young students do these things called splitting actions, which I don't know if you're familiar with. It took me a while to wrap my head. I still don't think I have completely, so forgive me. But splitting actions being listed there as sharing, folding, and magnifying. So young students, that those processes, it's multiplicative reasoning, dividing things and multiplying things, have an intuitive basis in young children. And so if you harness those intuitive ideas to do ratio early, essentially you're doing one of the major issues in maths education, which is moving students from additive reasoning to multiplicative reasoning. That's the general argument. Does that
Yeah,
make sense?
I find that rather difficult, though. That so in light of coming to this conversation this evening, I had a look at what we might see from research around this, and I came across a really nice paper, which I won't be able to provide the link to because it's on my iPad, but it was in Education Studies in Mathematics, and it suggested we should look at how these things like fractions and decimals had historically developed, and there's a good reason for thinking we should perhaps look at the history of how things in mathematics have been developed, given that sort of shows the sort of progression in thinking over centuries, and so it certainly wouldn't be that we started thinking around ratio. And why wouldn't you take children through the natural sort of development? It's not suggesting that you do it from a historical perspective, but you could see how that would sort of not really go where you're going with that paper, Lucy.
Well, no, I want to pick you up on that word natural, because I'm not entirely sure what you mean. I'm always suspicious when people use that word. What does that mean here, Jeff?
Well, I have thought about this in other instances, not in relation to fractions, but the development of mathematics is a really slow process. And when I say centuries, some of the thinking around fractions was from something like 1,500 BC. So we're talking now 2,000-3,000 years. And it would seem that a natural development in the sense of what happened. Okay, so historically what happened, mathematicians at whatever level were working and developed their thinking in a particular way that built on previous thinking. And clearly we started from counting, and there's a lot of research on counting, obviously, that's important. And then the next step was to think about then fractions. Where do they come from, and why do they matter? And so that's thousands of years ago now. But it would seem that wouldn't children appreciate developing in that sort of way that we historically had developed?
Well, Jeff, I want to come in on something here, if I may. Sorry, Lucy. Didn't, like, in my maths and things like that. Yeah, but in my reading of history of maths and things like that, didn't sort of the ancient Greeks and people like that basically treat fractions as the ratio of two integers? So it's almost a notation thing rather than a conceptual thing. Well,
I think you can see some of that in the sort of formal work of some of the mathematicians there, but I think there was an understanding more generally of fraction before that formality. And most young people from early years onwards do have some natural affinity with ideas of fraction in a reality that they understand. And I think one of the things when I've been looking at some of the work around fractions is it's quite abstract, the discussion of it. And young children don't want to be moved to the abstract too quickly.
So we're going to go into realistic maths education very shortly, Jeff, aren't we?
Yeah, we will do.
Not yet, though. Andrew, you wanted to come in on something there, I think, didn't you?
I have a lot of sympathy with the historical approach, but I do sort of, it's easy to look back and see this sort of progression of ideas through history and sort of miss all the wrong turns that were taken. And there's a lot of times where our current thinking of what something is there's been a definite paradigm shift from the historical development. And so thinking of what a fraction is, I think we would now, in sort of higher abstract maths, think of it as being quite different to how that progression has leads to it, the historical progression. And it kind of maybe, I wonder if there's an alternative way of doing it. It was kind of looking at how is fractions defined so formally, and can we like shadow that back down? I completely get the not wanting to be too abstract, but rather trying to find some way of thinking about fractions that foreshadows that and makes that transition to the more sort of formal mathematical way of thinking about fractions a little bit easier, without some of the sort of historical baggage that fractions have accumulated over the 1,000 or so years.
Well, I think another issue is that clearly the trajectory of learning would have to be carefully designed, and I'm clearly going to go for coherence in the curriculum, because that's a big issue that I've got with about a lot of what goes on. So you would have to make some decisions really carefully. Mm-hmm. That would allow you to develop it in a way that's coherent over the entire school curriculum in terms of fractions.
I guess what I'm wanting to say then is that should then be coherent with, should any of them go on to university or even further, that the story should be consistent with what they would meet there, so that when in university they meet fractions in the sort of more formal setting, it's not like, oh, this is completely different to what I thought it was, but rather this is the completion of the story that they've been told bits of before.
And so another thing I was thinking about was talking to a science educator a long time ago now, but it's quite clear in the science curriculum there are models that don't work, like you were just saying, that when you get to higher education, the model of the atom that you start with is absurd when you're working at a high level in university. So what struck me at that point when I was talking with him, as I say, a long time ago, is that just a minute, in science they just actually do teach things that are wrong, and but they all accept it, and there's a clear understanding of why they do that and where it's going to go. But in mathematics, we don't have that level of agreement, I think, as maths educators across the board, as to what it is we're going to do to develop this so that we get to the end points that we want to be at. And
that's exactly why I'm not a scientist, because I got to my A-level science, and my A-level chemistry teacher said, right, everything we told you in GCSE was wrong, this is the real bit. And we don't need to do that in maths. We can have, it doesn't have to be, we don't have to introduce fractions in the same sort of formal language, but it can be consistent with how they're thought of.
Well,
we don't need to lie.
Because my question is that one of the reasons for introducing the concept of ratio before anything else is how it's related to rational numbers, right? And this is about actually a really big conceptual shift towards numbers that look different, behave different than expected, aren't as intuitive for small children. And so this question of when is related to what and how. And so I guess the thing that I'm questioning is how much are we debating here different expressions of the same structure, or are we actually thinking of those different expressions as their own objects and entities, in which case, the ordering matters. So, saying ratio needs to be the lens through which you look at everything else and it needs to be the first thing is one argument. Saying it doesn't matter which, as long as you relate them all together, is another argument. And making the case for fraction being the first or percentage being the first is another thing entirely. But it does come down to, are they all expressions of one structure in maths? And what is that structure? Or do you see them as different but related entities?
And I'm going to come in with Gemma on that one, because Gemma and Will haven't had the opportunity to join the discussion yet. So, Gemma, I think sort of leading on from Lucy there, when you're teaching, fractions, decimals, percentages, are you treating them as separate things? Are you treating how does that feature? And do you think it matters which order we approach these things in with learners from your experience?
I think it always matters what order you approach things in, because whatever you introduce first is going to then have a knock-on effect on the way your pupils are thinking about anything else that you subsequently introduce. Which is actually, when Lucy was asking questions, I was pondering what it might look like and what the knock-on effects might be if you did start with ratio, because it's not something that I've ever considered myself. I do, when you're talking about the ideas of the same structure, I think generally I would consider everything through the lens of multiplicative relationships, and considering it with the idea of proportion as at the centre rather than ratio at the centre. But if you were then to say, take this idea of multiple relationships and start with ratio, I'm really curious, what would happen then? And what age are we talking? Are we talking from, like, children first meet fractions in, say, year 1, year 2? Are we talking starting, that is the idea from this paper starting that early? And if so, how would that affect what happens next? I'm kind of saying this as an open question, hoping people follow the thought process.
I can tell you what the paper says.
Go on.
The suggestion in the paper was there were 2 activities that particularly intrigued me. One was called, really imaginatively, Mr. Tall and Mr. Short. And the basic premise was it's the right way around. Mr. Short is 6 paper clips or 4 buttons high. And the other guy is 6 buttons high. How many paper clips? And it wasn't presented exactly like that, but that's the meat of the task, right? And that is definitely accessible to year 1. The task and understanding what the task demands, but the way that it's related to measurement and the units of measurement, and in particular non-standard units of measurement, is interesting to me and really grounded in measurement. And I don't see a way that you would do this without making these and really thinking about space and spatial ability in terms of that. And then the second one was about dominoes. They were looking at how many, and they physically did it, how many dominoes they could set up and knock over in a certain amount of time, and sort of generalizing that relationship. And of course, what's really interesting is it doesn't necessarily generalize, because they kept knocking them over before they got to the point where they wanted to knock them over. So I think it's a really interesting paper and lots of really interesting activities. And she certainly puts her money where her mouth is, where she designs the whole thing from start to finish.
So it seems from what you said that they're trying to start from this idea of a multiplicative relationship, rather than the kind of more standard British approach of a fraction being sharing a whole into parts, which I know obviously is ultimately a multiplicative relationship as well, but it seems to be that they're deliberately not focusing on it from that approach. Is that fair?
Yeah, and I think part of that is that the standard misconception when you start about sharing a whole into parts is not being able to reconceptualize that whole and getting fixed on what is the whole and not being able to change that fixed idea. It's one, it's a unit, it's a thing. And then when we start to do, more flexible things with fractions, we can't move away from that. And I think that's kind of interesting to me, that if we actually roll it back and say, what's the structure underneath here? You could argue it's x per y, which is kind of the ratio argument. But you do have to get underneath rate there, I think, which is quite interesting because they're not the same. And I don't know how important that is when you're dealing with very young learners, but it becomes more important later. The difference between something per something when it's the same dimension or the same type of quantity, or something per something when they're distinctly different, sort of comes out of that naturally. And that's really hard.
Well, there's also 2 different conceptualizations of fraction there, in the sense that you've got the fraction as a number that you could maybe place on a number line, or almost fraction as operator, and representing the relationship between 2 quantities.
Mm-hmm. And Gemma, you just pointed out the tricky shift, isn't it, from understanding the part to whole relationship to the position as a number, and I think that's possibly where a lot of children come unstuck. I mean, I can't remember way back when I was a kid, but how did kids make sense of this sudden shift? Now you just play with them as numbers in this mathematical world. And of course, that's what we do want, because we want to be able to operate with the fractions and in the number system.
So is that a case for starting conceptualizing fractions as numbers rather than as a ratio or as a proportion?
I think the difficulty lies in that shift. I think most kids understand the part to whole thing, and which is where the NCTM start now in all of their materials for mastery. But then how do you make that shift is the question.
But what I'm thinking is, Jeff, what if we were to turn it on its head and say that if we weren't to start with the part to whole, and we were to start with fractions as a number, and sort of the ratio of 2 integers comes later.
I think we can't get away from the part to whole relationship, because that's what I meant earlier about things that are natural. It is natural to understand part to whole, and everybody wants to be able to express that from quite an early age. I mean, you can't stop it. With your kids in the house, they're going to talk about things. Oh, you'll have to give your brother half or whatever.
Which brings us back to an earlier discussion I think we had, Lucy, doesn't it? Quite about sharing and fairness and kids' concepts of fairness.
Sure, but why can't we conceptualize that as a ratio? Because what we can do then is make it a relationship that's dynamic, not static. So it doesn't have to be you get half the cookie, your brother gets half the cookie. It is whatever I'm about to share, you will have one part to your brother having one part. And when the new baby comes, by the way, we need to change that. Well, isn't that interesting?
Well, we might be able to do that as maths teachers, but what I'm saying is that maths is not just in the maths classroom. It arises everywhere, which a lot of people don't believe. I just wanted to point out, though, your example that I'm not aware of her paper about this. The sort of the L. No, sorry, it was that the man being so many paper clips and so many buttons. That just reminded me of Dietmar Koopman's research item about different objects like that being scaled up, and of course when it goes to two-dimensional, so the two-dimensional, the L shape, that's where the problems occur. He finds that in linear situations the scaling can work quite straightforwardly, but when you come to 2 dimensions, it falls apart a bit.
Will, I'm going to come to you here now. In terms of a sort of developer of, video learning to support pupils and things like that, how does this sort of factor into that, and how do you make decisions about that content, and how does this relate to that?
Well, my first maths video that I did was all about fractions and just like really fundamental approach to fractions. And for me, I think the important distinction is very much about the context of how you visualize it. So, for example, for the fractions one, I did a classic example of how many slices of pizza are there in total, and then how many slices are you choosing. And so it's the difference, as someone that cares about it from a sort of visual perspective primarily, is all about the fact that a fraction is slices of pizza, for example, is very appropriate for a fraction. Something I was going to say actually earlier when we were talking about the difference between fraction as number on a number line and fraction as sort of a sharing, being able to share like I said about pizza, is almost that maybe you don't need to make the distinction between the two, because again, talk about it from a visual perspective, you could do both by having that number line, splitting the the gap between 0 and 1 into 5, and then choosing one of them, and one fifth along is 1/5. So you can sort of do both if you were to represent it visually at the same time, even though it's not using items like slice of pizza or whatever it is. It's still doing both of those, accomplishing both of those things with the same visual sort of aid.
I know a lot of maths teachers that would have a very large argument with you about slices of pizza, but I'm going to dodge that one. I'm going to dodge that one for now.
I'm interested to know what arguments.
Let's have the argument, Pete. Come on, we're all in secret.
I'm the most sort of amateur person within this chat, so I'm always interested to there's all these, like you say, as if it's sort of in the known, but I'm actually sort of unaware of this. So what's the
Go on, Pete, be difficult.
Oh, it's not necessarily difficult. I mean, there are sort of recognised, certainly I don't know how widely across the maths community because I don't know them all, but recognised potential difficulties with being able to split a circle. And being able to split a circle equally, particularly in certain bits. And, very often people now sort of talk about use rectangles and talk about, galaxy bars and box of chocolate and things like that, which are potentially easier to divide Equally, if that's the way we want to think about the fraction, dividing the whole into equal parts, it's potentially easier to see how the whole changes when it's a rectangle or when it's compared to when it's a circle, and make those sort of links spatially. So I know a lot of maths teachers that would argue for a move away from circles towards sort of shapes that are easier to see the change and see the impact in. If anybody else wants to come in.
Yeah, I'm happy to. I think all models have their advantages and disadvantages, don't they? And I think one of the problems is that people there was a bit of a resurgence of the circular area fraction model for ages, and it became just the trend. And obviously, every trend has a backlash. But one of the I think real big disadvantages was the thing that Jeff's described, this idea of dimension being really important, is I mean, circles, the area is notoriously difficult for humans to comprehend on any level. And we know this because of pizza problems and dinner plate problems and all sorts of things. And so thinking about your underlying conception, you know, what might be a smaller step from that? It's an array potentially, or something rectangular, which I have a bit more of a sense of why I'm moving from a kind of measuring along the line model to an area model, because essentially I can count the bits as well as think about the area as a kind of more continuous thing, I suppose. And the problem with the circle is it seems a lot further removed from that, and therefore has more complexity. I think that would be one of the issues.
Anecdote time. I was working with some students from the States. So we had a program where a number came over to the university every year, and I had a group of English students, predominantly Chinese students, and this small group of Americans. And I gave them some fraction work to look at. And it was really interesting because we're talking about cultural differences. And they said, "Oh, you can't cut pizzas into thirds. They come ready cut in eight slices." So that's just an anecdote, but it was quite interesting. The whole culture there was, "Hey, don't mess with our pizzas. You can't just start using them in fractions."
Well, you've got to pop to Morrison's and get one sometimes.
Yeah. So, but to go back to this number line issue, which of course I would come to, I go around promoting Japanese textbooks. They don't realize, but I would say their curriculum is incredibly well thought through and coherent. And when you are a teacher, you get what we would count as the standards, but you get underpinning that a lot of advice about how you should teach it. And they use number lines throughout, as right through to becoming Cartesian graphs, complex numbers, and so on. So they, those lines in Cartesian graphs are at right angles, obviously, but they do this really carefully. This shifting from the part whole issue to fractions, and they do it with number lines, and they do it with tapes, paper tapes, which are much more common in Japan than here. But they start by saying, so what amount of the tape have we got when we fold it into three parts and take one of them? So they start with that idea of a third, and then they position it on the number line, and they take that decision very carefully, thinking about where are we going to go with this when we get to decimals and percentage, well, not percentages, but they work that through really carefully. So there is no choice for the individual teacher if they're following a particular scheme. Some of the textbooks do it slightly differently, but it would mean that a pupil in primary going right through into secondary would have a clearly well thought through story and narrative of where fractions, ratio, and so on fit into mathematics over time.
Do you know off the top of your head at what kind of rough age they move part whole to thinking of a fraction as a number?
From memory, they do that in later than we would. They don't introduce fractions so quickly. They do everything more slowly, and they do less, and they do better in international tests. But they do that in, I think, grade 4 is probably the first time they start to think about that transition to number lines. And I'll say they'll bring decimals in much more quickly than we would. They're very, and one thing that strikes me is they're very focused on what is the unit. So the issue of like the pizza, which is problematic, but they will have what is a third of 2. If you've got a paper strip that's length 2 and you fold it into 3, then what have you got? And that would probably almost be an entire lesson, as the kids struggle to make sense of what they've done.
And as a maths teacher, that reflects, for me anyway, reflects back to the sort of questions, because I can't see from the experience I have of ratio, as a maths teacher and teaching ratio, that it would be appropriate to give the response to that using ratio notation. And I think this leads us into the sort of, it may well be still a ratio, but it doesn't seem to me that it would be appropriate to give the response to that in a ratio using a ratio notation.
You're taking
just
issue with the notation.
I am. Well, to me, that's what, when you say ratio, and when people say ratio, I see number ... number, or number ... number ... number. So, it may well be that it is still a ratio, but it's not being expressed as what I would consider a ratio, which I think leads us nicely into the second question in terms of, are percentages and extension ratio numbers at all? Because when I'm looking at something like what Jeff's just said, you tape of 2, you find a third of it, I can see 2/3 being an acceptable sort of numerical response to what I have. And I can see, potentially 0.6 recurring, if we're going to go with 2/3, being an acceptable numerical response to what I have. I can't really see sort of 66.6 recurring percent being an acceptable numerical response to the value I have, or, whatever ratio that would be, the ratio 2:3 or whatever else. Yeah, 2:3, or we'll get onto that in a third question, but I can't really see that being an acceptable numerical response. And we were discussing this on Twitter a little while back about our percentages numbers, and I was thinking, 2 divided by 5, if you asked a kid what 2 divided by 5 was, would you accept the answer 40%?
That's right.
Don't know what people want to
say. I'm going to say context.
Yeah.
Well, I was about to say, so if the answer to the probability question was 2 out of 5, would you be happy with 40% then? And if you'd be happy with it in the answer to a probability question, why would you not be happy to it in the answer of what's 2 divided by 5?
Well, I'm thinking purely numerically without context. And this is where Lucy and Jeff are going to...
I think we need to first figure out what a number is.
Well, go on then, Andrew. Take us in. We're going to first figure out what number is.
This is going on. This is something I'm thinking about a bit at the moment in my teaching, because I don't like to think of pi as a ratio. I like to think of pi as the area of a unit circle. But then you have to think, in introducing that, I should say a circle with a radius of a particular length with units, and then pi is like the area of the circle with that unit squared. But then how does that relate to pi being a number? So how does a number relate to a quantity? And they're subtly different. And I think this gets back to what Gemma, sorry, I'm trying to point to Gemma. Probably all in different places on your screen. What Gemma was saying about the idea of a ratio as being an operation versus a number as a quantity. And that actually I'm coming more and more to thinking that a bare number, even something like 2, should be thought of as an operation, and it's 2 of something. So when you say your 2 divided by 5 is 40%, it's kind of, context. Am I thinking these as numbers? Am I thinking these as quantities? And I kind of have different feelings depending on which one you want.
And the idea... Go on, Jeff.
So I just wanted to ask Andrew about, so would you teach the area of a circle as being pi, unit circle being pi square units, and would you and so do you do everything then through scaling?
Yeah.
And you do that with trig?
No, this is before trig. Oh, well, I do trig with scaling.
Would you do it with trig as well?
Yeah. So trig, so sine and cos are not ratios.
Right.
To be fair, Andrew, I do exactly the same thing with trig. teach it through scaling triangles.
So why don't you do circles like that then, Pete?
I guess because I never really thought about it.
I mean, I've just done this. I mean, I've just done this with one class at year 8, and we started out with working out the area of we did a quarter circle, and we did it by strips, cutting it up into strips, using Pythagoras to work out the height of the strips, and working it all out, basically doing integration without knowing that we're doing integration. And we're now just finding the circumference, starting with the area by doing differentiation. And of course, they don't know they're doing integration and differentiation, but that's what they're actually doing. And it just, again, it comes back to this idea of the consistent story of when they go on. So, for example, with trig, sine and cosine as ratios of sides of a triangle, it's really hard to connect to the circle. Sine and cosine as the lengths of sides of a unit triangle. Sorry, my hands aren't on the picture. Then that's much easier to then take beyond the 90 degrees into the circle as the coordinates of the points on the unit circle. So my story that I tell in year 8 then is consistent with the story I tell in year 12.
The only issue I had with that, because I do something very similar, but the only issue I had with that is that if sine of theta and cosine of theta are lengths, then they have dimension, and that affects the dimensions of the any calculation or whatever that you use them in.
Right. But
and it seems like that would seem that it would mess with other things.
Well, so then the dimension is specified by the length of the hypotenuse. So the sine and cosine are the lengths of the sides in a right angle triangle whose hypotenuse is 1 whatever. So it's 1, if you've got hypotenuse 1 meter, then the height is sine 30 degrees meters and the base is cos 30 degrees meters.
Yeah, but then if you then go and use them in, say, the formula half AB sine C for the area of a triangle, are you not then multiplying 3 lengths together, and should you not have a volume?
No, because one of those is a scale factor.
Which one?
I mean, because when because we're doing by similar triangles, you've got your reference triangle, and then you've got your scale factor, and this again gets back to is a number a quantity or a operator, and the scale factor is an operator. That's the hidden ratio, the scale factor between your reference triangle with hypotenuse of length 1 and your actual triangle with hypotenuse of length 5 meters. So you've got your scale factor of 5. So in the half AB sine theta, one of those is a scale factor and not a length.
Whoa, we're getting into something now, and I don't.
Right, but okay. I mean, there's a difference between, of course, how much of this I would explicitly say and how much is kind of how I'm thinking of it in order to make my explanation as coherent as I possibly can. So, yes, I'm saying to you, one of them's a scale factor. Of course, when I'm first talking about it with students, I'm basically sort of not expecting any of them to spot any of that sort of subtlety. But then in year 13, with a further maths student who might go, hang on, what's going on here? Then we can have that discussion.
Wow.
Why have you made the decision to do it that way round? Why have you made the decision to think of sine theta as a length rather than as a ratio?
Because I think that the most fundamental concept in geometry is similarity. And everything else stems from similarity. So if I can embed similarity at the heart of every concept in geometry, it provides a core that everything else hangs off. And
I agree with that.
Does treating sine, I was about to say, does treating sine theta as a ratio not also do that, though, by thinking of it as a scale factor?
But then it also then links then to the circle thing. So yes, but I think by treating it as a length, I'm trying to get them to draw a reference triangle with 1 sine theta cos theta as their sort of starting point of every problem. So you always have that reference triangle that you're taking everything back to, rather than saying this particular triangle, I've got my nice little formula, find the Socoterra. Oh my word, I hate that. And they're
Oh,
writing.
you see, I use that, but I use it to reference. No. But listen, I use it to reference the triangle. Sine is the opposite.
My
Sine theta is the opposite side when the hypotenuse is. Well, sine is the opposite side when the hypotenuse is 1.
Yeah. I mean, I will use the words opposite and adjacent hypotenuse. I just don't use the word Socoterra if I couldn't possibly avoid it. But that's more about mnemonics and no, that's more about when to use mnemonics and when not to, and that's a sort of different thing. I think.
I suspect that SMP did it like that in Book F, because I taught using SMP many years ago, and I certainly taught scale factors and sines and cosines and so on. So I will go away and look in my cupboard at my SMP.
Do you still have SMP stuff in your cupboard, Jeff?
I'm going to admit I bought them off Amazon in the marketplace, and they didn't cost very much, about £1 a book.
Wow!
But I'm not telling you that because if you all go and try and buy them, then the price goes up.
Correct. What we should all do is form an orderly queue, and Jeff can sell them out of a Macintosh to us.
Well, I mean, to be fair, there are only 6 people watching it, and the 6 of us, so that's a maximum of 12 people that got that message.
SMP Book B was the hard one to get.
Fair enough. Noted.
Oh dear.
But actually,
Lucy, you were going to take issue with something.
Right. I want to bring this back to specific stuff and slightly more general things, because we've skirted around the idea that students absolutely should have multiple conceptions of a fraction, and we were sort of talking about in which order, but we were saying a number on a line and as a part of a whole. And I see that. I mean, we actually, when we looked at this for the espresso, we settled on 6 rather than 2. And I'll tell you what they were, because I can't remember them all off the top of my head. But conceptions of a fraction roughly fell into 2 categories. One was sharing, so part of a whole, probability and quotient, and then measuring, which was number on a line, ratio or rate, and then operator or scalar. And what strikes me here is we're having this debate about, how to consider number as a quantity or an operator. And in my head, there's absolutely no need to make that dichotomy. And in fact, the more representations, the more multiple conceptions of a number that we can allow students to experience, while at the same time maintaining a sense of the identity of the thing they're looking at. Mathematically, that seems to make a lot more sense to me. So I'm just querying the general approach. Why isn't it okay to see all numbers as ratios? What's the issue there?
I have no issue with that.
Well, you should just go to the pub now.
I'm happy as long as you're consistent and it works across everything you want to do. It's when you flip to something else.
Right.
And so.
Okay.
Yeah.
So the idea that the ratio has an inferred operation. Now, that there is a problem because there isn't a single one, is there? And that's where we should get to this meaty debate. Like when we see a ratio written as Pete's suggesting in the traditional notation, and they don't have to be, but if they are, what's the inferred calculation that we are expecting students to see, and how do we expect them to see it?
So we're into the third question now, are we, Lucy, in terms of how do we read A to B in that notation?
So can I explain? I asked
that
question.
I'm reframing it. Yeah.
Sorry. I asked that question because I was we're doing a research project with GCSE research students, and we had a task where we asked them to share match some cards where a certain amount of money was shared in the ratio 1 to 2 between Ali and Blair, and they had some fraction cards, and they align the fraction 1 to 2 to a half. Almost 90% of these students do this. And likewise for 2/3 and so on. 2 to 3 would be 2/3 and so on. And I was presenting this with some colleagues from Europe in a research seminar, and they just didn't really understand what I found so puzzling about this. And because they said, no, but that's 1 to 2 is a half. And then so over coffee, I was trying to determine how widespread this was, and I would say, I mean, this is just totally off the top of my head, something like 2/3 of the people I spoke to thought of it as 1 to 2, and only a few of us saw it as 1 to 2 as a half, and only some of us saw the way that we do in this country, that you would share, one would get 1/3 and one would get 2/3, and that was just like quite astounding to me, which worries me slightly about international tests, but let's not go into all of that. So yeah, most of the students we're working with certainly see it as
See, I think I've misunderstood this question when it was sent through before. Are you saying then that the people you spoke to internationally actually would take that as giving everybody a half of the whole?
Well, they would. I haven't got to the bottom of what they quite think, but certainly A gets a half. I presume then B gets a half.
Yeah, because for me, it's really important that you've got the two different part and part whole conceptions from the ratio, but they're not contradictory. So the fact that one person gets 1/3 of the whole and one person gets 2/3 still means that the one of them has got double the other, or one has got half of the other. So that's all fine in my head. So I'm really intrigued to think that somebody might actually do something different.
But if you share £200 in the ratio 1 to 2 between two people, what's your understanding? Not that one of them gets a half of the money.
No, exactly. So one gets 1/3, one gets 2/3, but one has half of what the other has, and that's where the half comes in for me.
But it does for us.
So that's the bit you're saying doesn't happen elsewhere.
Well, we certainly have a different understanding of that. Yes, they didn't see it as problematic that our students were dividing the money in a way that we wouldn't approve of.
And so I think this ambiguity is the problem with ratio. I think that's why, to some extent, we introduced it late and we think it's hard. I think I'm planting most of the issue on the notation.
And it's a notation issue to some extent.
So how has our understanding developed differently to others then? Do we know this?
It's a what? Sorry?
I don't know.
Well, we're going to bring you back in here again because you've been very quiet for a while. In terms of, have you been creating videos around ratio and sharing in ratio yet? And what's your experience of that? If you have, we can't hear you, Will. No. You were quiet before, but now you are completely not there. No, you might want to try coming out and rejoining. That might fix the problem. It has done in the past, I think, with people.
No.
Oh,
1 minute.
Yeah, we got you then. Okay.
Can you hear me?
Yay!
Yeah. Okay, great. Sorry about that. I did a whole monologue about brilliant insight into all of this. It was just I was muted clearly. So yeah, something I was going to say earlier is that the difference between how you'd read ratio, do you think that could be influenced by the language that is used around how you read that? You've got it written out, you've got two numbers separated by colon. How do you actually read that out loud, and that being a way that its interpretation is influenced by that? So like 2 to 3 or 2 in 3 or something like that could potentially contribute as well. So instead of it being actually just a visual thing, an interpretation like that, it's also about how you then present that, reading it out loud, how you with the language that you use.
That's interesting, is it? 2 in 3. Do you get a sense, Jeff, that that's how they were talking about it in these countries where they saw it as 2/3, 2 in 3?
I wouldn't like to get to that level of
detail.
Well, language. What is interesting, maths is supposed to be universal language, but it clearly isn't when we're talking with people in other countries. and the subtlety between those sorts of words is not easy to work out, even when you know people really well.
Yeah.
I've just come across a really good
Lucy.
resource on this. I was doing some digging, and I'm part of a very elite group of people who went through my maths PGC through the Open University at a time when John Mason was writing materials. I thought it was special. Turns out he's been writing Open University's materials for a very long time, and I found something which I'll stick on Twitter from, I think it's 1988, so it's not older than me, but it's not far off, in which he very much, and lots of other people, talk about this issue of language. And the case is made that almost every exam question that students will come across, not exactly almost every, but a large proportion of, is a ratio or a rate question. And so the examination of language there is really interesting. And it's 2, 4, 3, 2 in 3, 2 for every 3, 2 per 3. There's about 10 different ways in which they examine language, and I think it's really helpful to start to unpick what's going on with the relationship between the quantities that's being examined. I'll put it on Twitter while you think about it.
I even think that it could sort of go down to the level of not just like differences in terms of like European countries and, you know, America, and, you know, from on a national level. Could it even be, I mean, this is getting really detailed into it, but could it even be in a regional level, especially given the fact that I feel like prepositions can be interpreted in terms of different dialects, can be interpreted differently. You know, obviously you've got the RP sort of how prepositions should be used, but then also in terms of actually casual dialect, prepositions used creatively or in different ways in terms of different regions in the same country could potentially be you know, contributing to it as well. So if you ask someone from you know, a city in the south compared to a city in the north or something like that, you could even then have differences within the same country.
I was talking to the head of physics only last year, actually, and he came to me and he said, I can't get my physics students to work properly with speed, distance, and on time. And he's saying, I keep telling them that speed is distance on time, speed is distance on time, and they're just not getting it right. You're Scottish. And I said, I don't think they understand the way you're saying it, actually, because I don't think anybody around here, I'm in the Midlands, ever would say distance on time. They would understand over. And that was what it came down to. The moment he changed his preposition, they were like, oh, okay, we get it now.
And also because of the preposition, you know, using the word over, for me, especially as a sort of, you know, as an animator, for me, I almost imagine over being that fractional, that visual fraction, that you've got one number. This is literally almost jumping over another number. And I always imagine that in my head, you know, 1/2 is literally 1 above the 2, and that's how I immediately connect that phrase to the visual representation of a fraction.
But that in itself causes problems, doesn't it? Potentially, because then you are seeing, you're very much just focusing on the fraction as the ratio of 2 integers and not necessarily the other ways in which you might look at it. And if kids embed that too early, does it mean that they then can't see fractions, ratios, decimals in another way? Jeff, I'm interested in something because I want to pick up on this more. Like, so in the past, I'm not saying I would have it now, but in the past, I would potentially have seen teachers and potentially even myself have sort of introduced the very idea of ratio in as sort of, you know, take the ratio 2:3, for example, as having some counters, putting 2 here and 3 there, or having, you know, 2 red counters for every 3 yellow counters or something like that. And I think you can see where the 2/5 would come from in that sort of way of representing and that sort of visual. So in terms of, you know, your experience of working with people on the continent and stuff like that, if they were forming a picture of a ratio in that way, or, you know, manipulating, you know, creating a ratio out of the manipulative in that way, what would that look like to them?
Well, I guess my honest answer to that is I wouldn't know. But at the very beginning, you mentioned the realistic maths education approach, which we've got to say something about.
Yes, we do. Go for it.
This is an appropriate point to do that, in that. So we've been developing some materials to work with these GCSE resit students, and clearly in the realistic maths education approach, the imagery, the representations are really important, and it's really important that they're developed in a way that they sort of map from a realistic situation. If you want the image of 2 to 3, then you want some realistic situation where the 2 to 3 is visual, and you can therefore see the sort of thing that you want. And I don't know how they do ratio in the RME texts and so on that have been developed over time. But I mean, I think the use of manipulatives, like you said, is a really important issue, that we move away from them too quickly. And one thing we found with it's quite worrying that we're working with students who've had 11 years of maths education in our schools, have got to the end of 11 years and they haven't achieved a grade that's deemed satisfactory for progression to various things. And so they have to resit GCSE. What they tell us is their experience is such that they've had all kinds of teaching and they just can't make sense of it. I've got a lovely piece of video of this young woman saying, really, I don't want to be told how to do this again. I want you to work with my understanding, and I think I'm nearly there, and I want you to help me put it right. And these students are very happy to use manipulatives. And I think we move away from those in secondary schools far too quickly, when these students really want them to do the sort of thinking that you've just sort of illustrated with, if you're splitting things in a ratio of 2 to 3, here's some things, do that and see what it looks like, and do the counting, as it were, of what's happening.
Well, you're definitely going to get no argument from me on that.
Yeah, but it is. I mean, I'm a bit sad about these students in lots of ways, given that they've spent so long doing maths and they come out very confused. And I think. Sorry.
No, I was just going to say I would hazard a guess here, and I'm happy to have anyone tell me to the contrary. But I don't think over the last 20 years many math teachers were actually at the secondary level were taught how to use manipulatives or how to teach with manipulatives. It wasn't my experience, and that was back in 2004, and my PGCE was wonderful, and it hasn't been an experience of many of the teachers that I've known come in. Yeah. But at primary and in primary education, they do seem to learn these things, and I'm curious as to why those things for such a long time don't seem to have been fashionable almost.
Yeah. And I've been involved in ITE over time at various points. And the first thing, I was very fortunate. We had the opportunity to refurbish a room. And one of the first things I did was buy the sort of primary school cupboards where you've got plastic boxes and you can put all the manipulatives in, and encourage students to use them, and then them to use them with their students. But it's as though there's not enough time. It's always I would say just slow down and do get the manipulatives out, and try to make sure children aren't embarrassed about using them. I think it's
the curriculum, please.
I don't think it's I don't think it's just a time issue, it's a snobbery issue, and I think what's really interesting is we had a really prevalent attitude that, and I sort of blame the CPA progression, and I don't blame that progression, I blame people misinterpreting the concrete pictorial abstract thing, because there was a sense in which I think probably when I was teaching about the same time as Gemma, when we went through PGC, that it wasn't necessarily that manipulatives weren't useful, it's that in order to become good mathematical thinkers, that abstraction meant that we should take away their crutches of the concrete materials, and we couldn't let children, use them for too long, because otherwise they'd become reliant on them. And the really good mathematicians,
or they're not doing the
didn't need
maths
any
properly
by the time they hit secondary.
There's a reason
that
I
was
I
one
call
of
my
the
blog
attitudes that
counting on my fingers.
But isn't that the case in some of the
Yeah.
high performing jurisdictions? I mean, I people talk to them about Singapore and bar modelling, things like that, but they say that by the time they get to secondary, they don't use those anymore. They don't need to. They can see it in their heads without having to draw it, without having to manipulate it, and they've made the jump, the leap to the abstract there. So why is it our kids can't make the leap to the abstract in primary school, and be ready for it by secondary school, where in other countries they can? Andrew, you wanted to come in?
Well, another sort of anecdote just on the idiocy of this kind of abstract as everything in your head as from kind of university level. I had this situation where a colleague was trying to work on something and trying to persuade other people that it was interesting, and it wasn't until we sat down and actually drew the wretched things and figured out a way of representing them on paper that he could kind of go, look, these two things, look, you can see the pictures, they are not the same. And it wasn't until we could actually just get these concrete visualizations that we could really start working on things. And every single talk in my area that we went to, you'd start off with drawing a donut, because that was what everyone had in the picture they had in their head. This idea that we have to sort of, I used to work on the most abstract things you can possibly think of, and yet we'd start every talk with drawing a donut, because that's what we all sort of the picture we all had in our heads. And this idea that you've got to kind of abstract everything so it's this weird non-physical construct in mathematics is just totally and utterly bizarre. And it's this kind of, you start very young counting actual things, you end up in university counting actual things, and yet there's this period in the middle where we want them to count, I don't know.
I think there's an interesting aspect of the work I've seen in Japan, in Japanese lessons. But clearly the focus is on conceptual development, but in the lesson there's a substantial amount of time given to discussing, students discussing with the class their mathematical reasoning and how they got to the answer. So the answer is not the issue, and quite often they're told what the answer is after a few minutes, but it's how you get to it. And so the discussion is around what your reasoning was, and can you illustrate that in some way, so that so they might use manipulatives, although they don't use a lot of manipulatives in Japan, but they might certainly use diagrams and so on to explain what their thinking was. So the discussion in the classroom is not just about getting the answers, it's about how you work things out mathematically, and then with the whole class, what's an efficient way of doing this? What's really a good way of thinking? And that by the end of the lesson, they'll have agreed on some good approaches, or one good approach to that sort of problem. So I think we're quite often perhaps downplaying this sort of reasoning and understanding and not making it public, and that we could do more of that.
We've got a couple of comments.
I was going to say, Jeff.
Go on, Lucy, you go first.
Well, I just wanted to agree with that. I was going to say I totally agree with that. Actually, this is a fundamental question about what maths is for and what it is. And if we think that there's a competitive model underneath mathematics where it's like, get to the best, be the best, get to the top the fastest, be the guy. And, if we don't think about maths as communication, then of course, yeah, if you can think in your head as much as you can do it as possible and, be super abstract, great. But if the model is actually we're trying to communicate something and work on it together, like be collaborative, which is most mathematicians' idea of what maths is, then the drawing, the visualization, the communicating, the representing, the stuff that Will does is like crucial. That's the glue that binds the community together. Because if I can't explain it to you, we can't make progress together.
So we've got a couple of comments come in from different bits. Mr. Gaskell, Mr. G teacher, on ITT placement, we learnt a lot from our mentors in the classroom. Knowledge breed knowledge, which is followed up by saying that trainees need to see their mentors using manipulatives with impact. But I think that's part of the problem, isn't it? Because the mentors themselves, as Gemma was saying before, you know, the people who are in a position to mentor haven't necessarily worked with them, haven't used them, aren't au fait in their use. And in fact, probably the people who mentored them in school as well. If we're going back to the sort of area 2004, I trained in 2005, so very sort of similar time. And I don't recall working with any sort of physical object beyond a calculator in my teacher training, either in school or, you know, in university sessions.
One of the big issues here is the fragmentation in our ICT system, and there are so many different routes into the classroom, and for some of them you don't even need to see a university, so you are solely reliant or dependent on learning from the people in school, and that's not necessarily a bad thing. It does limit your exposure to ways of teaching maths.
Let's put a big smile on Jeff's face, that one.
I'm saying nothing. That seemed to be another route into teaching, isn't there? The Institute of Teaching.
There is indeed, yeah.
What we need is another different route. That's exactly what we need.
Exactly.
Well, the jury's out on whether that'll be a different route. Isn't that just PGCE by another name?
Who knows? but what we need is more time for beginning teachers to spend learning some maths to start with for the classroom.
Yeah, and obviously in terms of the early, I mean, we're going way off topic now, but the early careers framework is potentially a good step in the right direction for that. But even then, sort of having to teach 40 hours in the first year per fortnight and 42 in the second year, or, you know, 20 and 21 out of a potentially 25, doesn't give you an awful lot of time for that depth of development, does it? Lee Overy, who I know and I work with in Leicestershire as well, and their school work out of the Singapore sort of materials. They have the translated Singapore textbooks as well as the sort of English version of them from OUP, saying there is almost no evidence of bar models in Singapore textbooks, but algebra discs are a common thread. So there is some, and that was secondary textbooks he meant rather than all textbooks, because they're more prevalent in primary apparently. But so there is still some nod to sort of manipulative, but one would argue that algebra discs are potentially a more abstract manipulative than something like a bar model. Is that a bridge into partial abstraction? Lucy's just grinning at me.
Well,
No?
it's an interesting distinction, isn't it? I mean, I don't know why it matters.
Do you want to elaborate? Don't know why it matters.
What's the goal? Yeah, well, because we're coming back to this. I mean, saying that a manipulative is more or less abstract implies a continuum of abstraction. The end goal there, no manipulatives, right? Is that what you're saying?
I don't know if it's a goal. It might be a state. An end state is potentially working purely symbolically.
Can I pop something in here which I thought of from this conversation?
Go for it.
I personally, throughout school, struggled to complete the square without stopping and thinking very carefully about what I was doing. For some reason, it was just one of those things that I always had to stop and think about. The moment I saw it done with algebra tiles and an area model, I was able to just instantaneously see it and not work through it algebraically. So I would say that in my own mind, I have gone from being a successful mathematician and struggling with something that you might class as a pure abstraction, if that's probably not the right thing to say, but you know what I mean. But then I have gone, if we use this, we've all seen that this is not a continuum, but just to kind of use this idea, I have gone now back along the continuum, but in doing back to something more pictorial, but in doing so, I have improved my understanding of what's going on, and I have made myself more fluent in performing that procedure. So I would say that it's absolutely not a continuum that you have to go from concrete through to pictorial through to abstract, but actually it's perhaps different ways of conceptualizing the same idea, and some ways are more useful than others.
So I would say that in my sort of philosophical understanding of mathematics, then this idea of abstract as being somehow deeper than all the others doesn't fit with how I see mathematics. And what you just described is more that you're connecting. My camera's the wrong way around for me, so when I keep sort of so you're connecting like a geometrical picture of completing the square with an algebraic, and I'd say that connection is the abstraction. And so actually, yes, you felt like, it feels like you were saying you felt like you were going back along the scale, but actually by building the connection, you're going further along the scale and being able to make those connections and see completing the square as a geometrical thing, as an algebraic thing, as a something else type thing, in terms of the graph of the quadratic, in terms of the area model, in terms of just the pure algebraic manipulation. That's the abstraction, not being able to do it in symbol form without necessarily having any knowledge of what it is you're doing. Does that make sense?
Yeah, totally.
Thank you very much. Right, we are we've gone over the hour by a good 10 minutes, so we're going to wrap this conversation up. So I'm going to come to each of you now just for a final sort of, are fractions, decimals and percentages just ratio? Try not to sit on the fence. You can qualify and you can add context, but try not to sit on the fence here. So I'm going to take them this way. So Will, first, go.
No, because I think it's just 4 different sort of contexts of the same thing. It's 4 different representations. Again, thinking as someone that is, a visual sort of person, it to me just feels like 4 different ways of approaching the same thing. So, saying that they're all just ratios, my mind immediately goes to, well, why is ratio the one that's picked as the dominant one, sort of thing? So I'd say no.
Thank you very much. Andrew?
Okay, I'm glad you came to me after that, because I'm going to say why I think ratio is the dominant one, and that's because it puts the emphasis on the operational nature of it all. And so I'm going to take issue with the word just in saying that they're just ratios. I'm saying ratio is the bigger concept that those are examples of.
Okay. Not sure that was entirely not sitting on the fence, but I'll give it to you. It seems enough of a position.
Yes, they're ratios, but ratio is so much more than that. Because ratio includes the operational, it makes the operational nature of it all that much more evident, and therefore is the superior notion.
Thank you very much. Jeff?
I'm thinking of sitting on the fence, but I think the important thing is these are really important issues that we work on in maths education and throughout school. And so it's really important that we don't just subsume everything into something that works for us as teachers. The students need to understand each of them separately in different ways, particularly because of the way we assess them. And I am attracted to having a very clear underlying idea of what we're doing over time, what I would call coherence. And so if you want to start with ratio and have that as underpinning everything, that's okay. But that we've got to make sure that works for the students as well as us. I think quite often as teachers, we quite like this sort of uniformity and making everything, as I think about as coherence. But we've also got to give room for the quirkiness of percentages, for example. We've not talked about percentages, but they're a particular bugbear, I think, for lots of kids and lots of adults as well. And we need to bring those out away from ratio to make sense of them in the way that they work in our lives.
Brilliant, thank you. I thought there you were going to go for a proper politician's sort of answer, which was, your question is a very interesting question.
Oh.
And that's my answer to the question. But you rescued that very well, Jeff. Thank you.
I just hate it when they say, that's a very good question. They're just playing for time then.
Well, I thought that's what you were doing early doors, but then you've got into something quite nice. So well done. Gemma?
I really don't want to be drawn down the line of a false dichotomy or anything like that. But what I will say is, if by ratio you don't mean A:B and you mean multiplicative thinking in all its various forms, then I will say yes, they are.
Thank you very much. Lucy?
So my answer to my very stupid question is probably, but I don't care. And we've luckily got onto the thing that I do care about, which is that, to me, they're all instances of the same big structure that's really important. I think Gemma touched on it. I might call it proportional reasoning or multiplicative thinking. But what I really care about, we absolutely got to, and I'm so excited, is about being able to advise and represent relationships differently in maths, and not suggest that's just one step on a journey to doing proper maths, but actually seeing, representing and visualizing maths as practicing maths. And that's partly why I'm so excited Will's here, but also this issue is huge. This is actually about the democratization of maths. This is about people who are drawing pictures of maths, not being consigned to the corner and saying, oh, you're just doing doodles, that's not important, but saying, oh my God, you've done a really interesting representation of a relationship. I could call that a ratio. It doesn't matter. What they're doing is interesting to me and important, and that sort of sense of communication is more interesting, I think, than what we call it.
So that is sitting on the fence then.
No, I mean, it doesn't. I don't care. Is the answer. Call it that if you want. It's fine. I'm happy with it.
Okay, fair enough.
I mean, Jared Collins knows their stuff. Cool.
I'm still leaning towards no on this one. I think that there are aspects of fraction, decimals, and percentages that speak very well to that proportion, but I'm not necessarily convinced that that's all they are. And that there's not something else there that communicates something that isn't just about a proportional nature. So I'm still going to go for no, but there's been plenty to think about. So I'm now going to read my mandated, and I'm saying this under duress, people out there, my mandated by Lucy. Not at all mandated. Not at all mandated. One of the
country's finest comedians.
So, as always, thank you for joining us this evening for our curriculum convo. I've been Pete Mattock, apparently the King of the North, and she's been Lucy Rycroft, mother of dodecagons. And remember, in the game of cones, you either remember to divide the height by 3 or you die of shame. See you next time. Thank you very much. Thank you very much to our guests as well for joining us. Very interesting conversation. Have a good evening, everybody.